Okay, in this first video, and there's going to be two, the first video kind of explains the Pythagorean identities, how they're derived and how you can manipulate them, because most likely what they're going to be doing in this class is they're going to be using these to simplify expressions and possibly to prove identities. Kind of like back in your geometry days when you had proofs and you had to show that one thing led to another. So we're going to start off with the idea of a unit circle. The unit circle means the center is 0, 0, and the radius is 1. Now I didn't draw the whole unit circle, I just drew the first quadrant so that I could draw a specific triangle in here. This is very arbitrary, but this particular triangle here is set up so that it has a central angle of theta, right? It's in standard position. This is the terminal side here in purple. And it intersects a point on this curve somewhere, on this circle, x squared plus y squared equals 1. I don't know what it is, I'm just going to call it x and y. And we know that when you're using the unit circle, that the cosine of theta is the x value and that the sine of theta is the y value. Now, if you have a circle with radius r, something other than 1, then you have to divide x and you have to divide y by r, because then you've got adjacent. Remember, this is your x value here, and this is your y value here. You would have adjacent over hypotenuse or opposite over hypotenuse for sine. Now, if I take the equation of the unit circle and I brought it down here, and I replace the x with what the x is equal to, which is the cosine of theta, and I replace the y with what the y is equal to, the sine of theta. So I have the x as the cosine of theta and the y is the sine of theta, right back here. And if I plug those in for x I have the cosine of theta and that gets squared, and in for the y I have the sine of theta and that gets squared. I get this equation here. Now this is a little awkward, this is hopefully a little bit more convenient and won't mess you up, but when you write a trig function to a power, all you have to do is either put parentheses and put the exponent on the outside, or you can get rid of the parentheses and bring the exponent in between the name of the trig function and the angle. So this is cosine squared theta, which is the same as cosine of theta squared. So when you say cosine squared theta, it means the same thing as cosine of theta quantity squared. Same thing here with sine of theta quantity squared, it's the same as sine squared theta. That's how we read that. So I get cosine squared theta plus sine squared theta equals 1, and that is the most important out of the ones that I'm going to talk about here, because it's the most common. This is a Pythagorean identity. No matter what angle you put in here, now you'd have to put the same angle. You could put like 30 degrees in if you wanted to. In fact, if I plug 30 degrees in and I write cosine squared of 30 degrees plus sine squared of 30 degrees, does that equal 1? Well, the cosine of 30 degrees from the unit circle is the square root of 3 over 2. That's going to get squared. And the sine of 30 degrees, again from your unit circle, that's a half, and that's going to get squared. When you square the square root of 3 over 2, you multiply it times itself. Square root of 3 over 2 times square root of 3 over 2 is 3/4. 1/2 times 1/2 is 1/4. 3/4 plus 1/4, that's 4/4 or 1. See, it's true, no matter, not just for 30 degrees. This is an identity, so this is going to be true for any angle you put in. You just have to put the same, you can't put like 30 here and 45 here. It has to be the same angle, same variable. Okay? And that is the first of the Pythagorean identities. And that's the one that I just flat out memorized. Now, there are two more versions of the Pythagorean identity. And I'm going to derive both of those now. And this is how I used to remember when I was first learning this stuff. Now I've kind of got it memorized. But if you take the original Pythagorean identity, cosine squared theta plus sine squared theta is equal to 1. And if I divide both sides by the cosine squared theta, so that means I've got to divide every term on both sides by cosine squared theta. So I have cosine squared theta over cosine squared theta. Well, we know that's 1. I have sine squared theta over the cosine squared theta. Now that's the same as the sine of theta over the cosine of theta squared. And then over here I have 1 over cosine squared theta, so that's the same as 1 over the cosine of theta squared. So I end up with, if I take the sine of theta and divide by the cosine of theta, that's tangent. So I have the tangent of theta, and that gets squared. And then 1 over the cosine of theta, that's the secant of theta. and that gets squared. Or we can use the notation that I was showing you before how to put the exponents. I have 1 plus tangent squared theta is equal to secant squared theta. And that's the next one. That's a Pythagorean identity, and that's a Pythagorean identity. And they're called Pythagorean identity if you haven't already figured it out, because it's all based on the Pythagorean theorem for the right triangle. Now, if I go back to the original here, and I take cosine squared theta plus sine squared theta equals 1, but this time if I divide both sides by sine squared theta, so that means every term on both sides gets divided by sine squared theta, I have cosine squared theta over sine squared theta. That's the cosine of theta over the sine of theta squared. And of course sine squared theta over sine squared theta is 1. And I have 1 over the sine squared of theta. That's the same as 1 over the sine of theta, the whole thing squared. Cosine theta over sine theta is cotangent theta, and that's squared. Plus 1 equals 1 over the sine of theta. That's the cosecant of theta, and that gets squared. Or again, using the a little bit better, a little bit simpler, quicker notation, cotangent of theta squared is cotangent squared theta plus 1 equals, you got it, cosecant squared theta. And that is the third one. Now, if you memorize this and you look to see how I derived these, it's easy to figure out the other two, or you can just memorize them all. But those are the three Pythagorean identities, and remember how often you use the Pythagorean theorem in geometry. Well, you use the Pythagorean identities in trigonometry at times just about as much. Now, the last thing I have over here, and I haven't gotten to a sample problem yet, but the last thing I have over here is I want to write each Pythagorean, oh, I forgot the word identity, each Pythagorean identity, if I can spell it, two other ways. Two ways. So I start with the cosine squared theta plus sine squared theta equals 1. So first off, cosine squared theta plus sine squared theta is equal to 1. What if I was to subtract sine squared theta from both sides? Then I would have cosine squared theta is equal to 1 minus sine squared theta. That's a good way to, because sometimes what ends up happening is you'll see this expression and then you can substitute this in for it. Now it comes directly from the first Pythagorean identity, but you should be able to look at this and visualize this by subtracting sine squared theta from both sides and know that this is also an identity, it's a true statement. Now if instead of subtracting sine squared theta from both sides, what if I had subtracted cosine squared theta from both sides? Well, if I subtract cosine squared theta from both sides, very similarly, I'm going to end up with sine squared theta is equal to 1 minus cosine squared theta. And these two variations of this guy show up a bunch. You're going to need to know that one, okay? Lots of stuff to kind of keep track of. That's the bad thing about all these identities, is that they're all important at one time or another, and so it's important to use them. You might only use them a few times. These you're going to use probably more than just a few times. So that's the first Pythagorean identity, and notice that I did a couple things here by subtracting one term from both sides, two different ways here. So that's one way to rewrite, or two ways to rewrite the initial Pythagorean identity over here. Okay, I did put a star next to it. I'll put a star in there. Now let's go to this guy. If I start with 1 plus tangent squared theta equals secant squared theta, one of the most common variations of this is if you subtract tangent squared theta from both sides. Because what happens here is I get 1 equals secant squared theta minus tangent squared theta. Well, if I ever come across this expression, this is a much simpler one to work with. I would just replace this with 1. Just like if I ever came across cosine squared theta plus sine squared theta, I would just replace this with 1, because they're equivalent expressions. Now, if instead of subtracting the tangent squared theta from both sides, oh, here, let's call this number 1 here. The second one, what if I subtracted 1 from both sides? Because that might happen. And if I subtract 1 from both sides, I get tangent squared theta is equal to secant squared theta minus 1. So that's two variations of the second Pythagorean identity. And it's very simple to find. I'm just subtracting one of the terms, see the side with the two terms. I subtracted this first, got this. I subtracted this, got that. All right, one more to go. And that's this guy down here. Now, out of all three of them, this is probably the one that's not used quite as much. Nothing against cotangent and cosecant. It just seems like most of the identities that we work with are terms of sine, cosine, and tangent. So in this case, very similar to what I just did here, up here, I'm going to take this guy and I'm going to subtract cotangent squared theta from both sides. Okay? If I do that, these will cancel. I'll get 1 equals cosecant squared theta minus cotangent squared theta. This is a good one to remember. Because again, this expression simplifies all the way down to 1. If this came in to an expression you were trying to rewrite and simplify, you could plug in for all of this, you could plug in 1. Another thing that you could do here is instead of subtracting that, maybe you subtract 1 from both sides. That would give me the cotangent squared of theta is equal to cosecant squared theta minus 1. Now, I have 3 and then 6 more. You say, I can't memorize all 9 of these. You don't have to. If you memorize this one, and then the steps to get the other 2, and then these are just subtracting a term from both sides, you can try to bring back to memory at any given time all 9 of these. But you've got to know this one here to begin with. This is the most important one. Start with this. And this is easily derived, as you can see, from this right triangle and a couple of substitutions in here. All right, now we're going to try some examples next. If you haven't already tried those, I think they're on the second page, then my suggestion is look off the first page until you can rememorize these things and then use these to make substitutions. Now you still have to remember stuff like that the tangent of theta is equal to the sine of theta over the cosine of theta, and that the cotangent of theta is equal to the cosine of theta over the sine of theta, and that the secant of theta is equal to 1 over the cosine of theta, and the cosecant of theta is equal to 1 over the sine of theta. Those are never going to go away. You need to remember those. But here's some more identities for you. Besides, these are sometimes called the quotient identities and the reciprocal identities. There. All right, well, we're going to try some problems in the next video.